Hi, everyone, again. In part 3 of the lecture, we're going to see another example of a differentially private algorithm called the Laplace mechanism. This is an algorithm that's a basic building block of lots of other differentially private algorithms, and we're going to be coming back to it over and over through the semester. Our starting point is pretty natural. So suppose we've got some function we want to compute on our data set, and we want to release, we want to add randomness to that computation in some way in order to release a result that's close to the value of the function and somehow satisfy a concept like differential privacy. Okay, so suppose we've got some summary in mind, some function f that we want to compute. So it could be something simple like the proportion of diabetics, this thing we've been talking about over and over. But it could also be something a lot more complicated. It could be maybe a covariance matrix, or maybe some machine learning model that's been trained on our data set. And it could, so it could be like a long list of statistics separate that we think of computing separately, or something sort of some long vector that we compute based on the entire data in some complicated way. All right, so we want to add noise, and the thing we want to understand is how much noise do we need to add to satisfy something like differential privacy? And furthermore, how does that depend on the structure of the function that we want to compute? So the driving intuition for this algorithm is that we can release f of x accurately. That is, with relatively little added noise. As long as f is not too sensitive to individual entries in the data set, to changes in individual records. Okay, so we want our algorithm overall, we want its distribution to not change very much when we change one record. And so a natural thing to look at is, well, how much does the function change? This function we want to compute when we start messing with individual records. Okay. So one way to get a handle on that is via what's called the global sensitivity of the function. It's actually the L1 global sensitivity of the function, and for reasons we'll see soon. Sorry, that should be easier to read. So this is what we'll define the global sensitivity as the maximum change we can see in the function between two neighboring data sets. So we'll consider the maximum or the supremum over all possible pairs of neighboring data sets, x and x prime. And we'll look at the f of x is some vector of statistics, f of x prime is some vector of statistics, and we'll look at some measure of how far apart those two vectors are. And specifically, we're going to use the L1 norm. So the L1 norm is, the L1 norm is the absolute value, the sum of the absolute values of the entries of a vector. Okay, so that's sort of a fancy notation for just meaning we're going to, subtract, look at the difference between f of x and f of x prime, take absolute values. So in every entry, that vector is now positive or non-negative, and then add everything up. And that's the measure of how far apart the two vectors are. Okay, so for example, for the proportion example we saw before, well, that's a one-dimensional function. In one dimension, this norm is just the absolute value of the difference in the values of the function between f of x and f of x prime. So the proportion, if I change one person's record, they go from either diabetic to not diabetic, or the other way around, from not diabetic to diabetic. The proportion of diabetics will then change in absolute value by at most 1/n. So we can think of this global sensitivity as some measure of how much the function f sort of smooshes or spreads apart data sets, how it converts distance in data set space. So, the green blob here is, data set land, and how it converts that distance between data sets into the natural, this distance between vector values of the function which is the L1 arm. Okay. So the intuition is that the less the function tends to spread things apart, the less noise we have to add. And indeed, that is true, or at least it's sufficient to add noise proportional to this thing. So the theorem is that the following algorithm is differentially private. What we can do is we can take our function value, so that's a vector, and we can add independent noise to each entry of this vector according to what's called the Laplace distribution. And the amount of noise we have to add is proportional to the global sensitivity of the function. So that's the measure of how much it varies when we change one entry, divided by epsilon, the privacy parameter. So the more sensitive the function is, the more noise we have to add, the stronger a privacy guarantee we want. Again, that means epsilon's going down, the more noise we have to add. So this isn't the only way to satisfy differential privacy, as we know, but this is one reasonably good way for many functions. What's this Laplace distribution? So the Laplace distribution is pictured here. The density function is drawn here on the plot. So it is it's a probability distribution on the real line. Its density has this form. So it scales with the absolute value of the argument. So the density is if you run it with parameter lambda, then it's 1/2 lambda times e to the minus the absolute value of the argument over lambda. So what's really going on here is that the sort of all lambda is doing is just rescaling the distribution. So lambda is just sort of the measure of like roughly how spread out the distribution is. So that is this kind of rough magnitude of the noise you're going to add is going to be given by this global sensitivity over epsilon. And just, to give you a concrete sense, the standard deviation of this distribution is lambda times square root of 2. Okay, so roughly speaking, it's very close to lambda. In fact, it's also true that the expected absolute value of a random variable with this distribution is exactly lambda. So the lambda is really a good measure of like the scale on which you're adding noise. And what this tells us is we can add noise that's proportional to the global sensitivity and that is also proportional to 1/epsilon. And we can do this sort of independently. We can add noise independently to each entry of the vector of the function value. Okay, so let's just see some examples of how to use this, just to kind of get a sense of what this algorithm is doing. Let's see an example of how to do this. So one function that's actually, maybe before we even get to those, suppose we're going to use this for releasing the proportion. Let's say f of x is just the sum of xi's, and the xi's are bits, okay, proportion of diabetics or whatever. Then we said the global sensitivity of f is 1/n. I'm sorry if this is the proportion of diabetics. And so what we add noise that scales with 1/n times epsilon. Okay, so the larger my data set is, the lower the noise is. And if you just compare to randomized response, the scale of the noise was actually 1/square root of n times epsilon. Okay, so the amount of noise added by randomized response for large n is really much, much larger than the amount of noise added by, or the amount of error added by in the estimate you get from randomized response is much, much larger than the amount of error you get in the estimate from the Laplace mechanism. Let's see some other functions that for which this mechanism really works well. Okay, so one example are histograms. So what's a histogram? We're going to imagine that our data universe, script X, is partitioned into d-disjoint bins. So we can somehow write this data universe as a union of different sets with no overlap in the BJs. So that BJ intersect BK is equal to the empty set for all J different from K. Okay, so we're just sort of splitting up the data universe into a bunch of pieces, D pieces, and our function is just it's the histogram of how many points land in each of these pieces. So it's a list of counts, 1 and 2 up to ND, where NJ is the number of indices I such that Xi is in BJ. So that's the function we want to release, and we want to add noise to that thing. Okay, so our function, if the bins were intervals on the line, the function would look like a traditional histogram plot that you might generate like in Python or something. Okay, so what we want to release is this whole histogram, and now we want to ask, what's the global sensitivity of this function? Well, if we consider neighboring data sets, X and X prime, they differ in one record. Okay, and so what's going to happen is that if one record has changed in this data set, what's happening is we're sort of taking one little, one contribution to the count of one bin, and either we're moving it to the same bin, or we're moving it to a different bin. The worst case, we're moving it to a different bin, so maybe it's going over here. Okay, but in either case, at most 2 entries change. Between X and Y, and when they change by at most 1. So if I look at the L1 norm of the histogram on X minus the histogram on X prime, that vector is going to be sort of a bunch of zeros followed by a 1, and then more zeros, and then maybe a -1, and then more zeros. In any case, it's going to have L1 norm at most 2. And so the global sensitivity of this histogram function is actually exactly 2. Okay, so as a result of that, what we can add noise, add Laplace noise on the scale of about 2 over epsilon to each entry, regardless of the number of bins in our histogram. So the amount of noise we're adding per entry basically doesn't change with as the number of histograms, as the dimension of the histogram increases. Okay, another thing we could look at is a sequence of what we'll sometimes call statistical queries. So these are just counting queries, counts. Oops, sorry. So suppose we're given, so these are statistical queries, which are really just fancy word names for averages of bounded functions. Average. Okay, so imagine we've got functions phi1 up to phi d, where each one maps records. Each phi j goes from x, it maps a possible record to a number between 0 and 1. So for example, maybe we've got, maybe where phi takes the record x and extracts like the income for that, like a tax form or something, normalized to lie between 0 and 1. And then so for each of these, we get a function, for each j, we get a function fj, which is the average of this function phi over the data set I equals 1 to n of phi j of xi. Okay. So this is just an average of a bunch of terms. Notice that if I change one record in the data set, this average changes by at most 1 over n. So the global sensitivity of this one average so the global sensitivity of fj is going to be at most 1 over n. Okay, because when I change one record, I change at most one entry of this average, and I change it by the sum changes by plus or minus 1, by at most 1, sorry, and that means the average changes by at most 1 over n. But what I'm interested in is releasing all of these, all d of these. So what I'm interested in is releasing f1 of x, f2 of x, up to fd of x. And now the global sensitivity of this thing, for two neighboring data sets, x and x prime, f of x minus f of x prime. This could be a long vector. So it's a long vector. I mean, it's length d. But each entry can be anywhere between between minus 1 over n up to plus 1 over n. But they can all be non-zero at the same time. So this is just some vector in minus 1 over n to 1 over n. And so its L1 norm can be as large as d over n. And so the global sensitivity of this f is d over n. Okay, which is still pretty reasonable as long as d is not too big, right? As long as the data set size is much larger than the number of these things we want to compute. Okay, so this leads us to noise, something like d over n epsilon per entry. So as long as epsilon is not too small and n is pretty big and d is not too big, then we get like a reasonably accurate estimate of each of these d averages. Okay, so those are a couple of examples of the Laplace distribution. Before I want to get through I want to explain why it satisfies our notion of differential privacy and why the Laplace distribution specifically is the thing that works here. But before we do that, like maybe one thing that's useful to look at is how this compares to randomized response, maybe like numerically. So what we've done is we've set up a sequence of experiments where in this particular experiment, we're interested in estimating just a single proportion, as before. And for simplicity, we'll assume that the data is generated IID, so the entries the entries are each like a separate coin that's flipped independently. It comes up heads with probably 1/4 and tails with probability 3/4. Okay. So what I'm interested in doing is trying to estimate the the distribution, the fraction of heads in the underlying population from which I'm sampling that are coming up, the fraction of people whose sort of bit is 1. And so like one thing I can do is I can simply take my big data set, and if I don't care about privacy, what I might do is look at what fraction of people in the data set have a 1 or a 0, and ask, like, is that close to a quarter, right? And so as n increases, the fraction of people whose the standard deviation of the sample mean, the number of people who have a 1 in the data set, that will get smaller and smaller, and that's the blue curve that you can see on this plot. It's sort of partly obscured by the orange one, but it's there. And then the other two curves are like how much noise you get from running the Laplace mechanism. Again, as an estimate of this underlying this number 1/4 that we're trying to estimate. And on the green curve, how much noise you get with what the standard deviation of your estimate is using randomized response. So as you see, randomized response, but all of them are kind of reasonable when when your sample size starts getting big, like at n equals 2000, even randomized response isn't doing too badly. It's sort of giving you an estimate that's somewhere between 0.2 and 0.3. But the thing that ignores privacy completely and the Laplace mechanism, they both start giving you these kind of estimates at a much smaller sample size. So actually the right point to compare, this is the blue, and the comparable point on the orange curve is this one. So that's like, that's how much error you get with, that's n equals 100. I think, and about 100, no, well, roughly. And then if you wanted to compare like at a slightly larger sample size, you'd compare like this orange point with this blue point. Okay, so what you see is that they're tracking each other pretty closely. And in particular, if you want to get an estimate that's differentially private, you only have to increase your sample size a little bit when you're using the Laplace mechanism, and you'll get like as good an estimate as you would have gotten with no privacy constraints at all. Okay, so maybe another plot that helps visualize what's going on is, imagine that this is for a specific sample size. This is n equals 100 actually. And this is epsilon equals 0.5. And what we're looking at is, if we just run the experiment, just fix the sample size n and run the experiment over and over lots of times, what sort of distribution do we get in the estimator, right? So again, the quantity we're trying to estimate is over here, so it's 1/4. The green distribution is the distribution of the regular sample mean. The orange distribution is the distribution of the sample mean. It's the distribution of the sample mean plus Laplace noise, and you'll see it's very similar. It's not quite as tightly concentrated. Tightly concentrated as the green distribution, but only a hair wider. And then then the blue distribution is what you get out of randomized response. It's kind of the discretization, the fact that the bars have spaces between them, that's due to the fact that there are only 100 possible different estimates you can produce because using randomized response. And so you don't get like a smooth distribution, you get these kind of spaces. But we see some interesting things. First of all, with randomized response, you're adding way more noise. But the other thing is that, sometimes if you're not careful, if you sort of do randomized response in the straightforward way, then you end up sometimes producing estimates that are actually like less than 0, and there's even some chance that you produce estimates that are greater than 1. And so, you're in this regime where you have to be much more careful about how you interpret the result you get. Okay, so the Laplace mechanism is definitely beating the pants off randomized response in this particular experiment. Okay, so that in mind, let's try and understand why the Laplace mechanism satisfies differential privacy. So again, what's our mechanism? Just to remind us. So we're given f So we've got this quantity, which is the global sensitivity of f is the sup over x and x prime neighbors of the L1 difference between f of x and f of x prime. And then we've got our algorithm itself, which takes f of x and adds independent Laplace noise in each entry, where Zj is distributed as Laplace with global with parameter global sensitivity over epsilon. Okay, IID. Okay, so let's let's prove our main claim that this mechanism satisfies epsilon dp. All right, so how do we do this? Well, let's start by fixing neighboring data sets x and x prime. Okay, and they live in whatever space the data lives in. And now what we're going to do is we're going to sort of proceed similarly to the way we did with randomized response. We're going to look at the probability, or more formally the probability density, with which some particular output is produced. Okay, so let's write down the density, the probability density of a run on input x. So it's going to have, we'll call that h sub x. And on input some vector y in r to the d, right? So so the algorithm produces outputs in r to the d. Right? So the density, what this is, because we're adding noise independently to each entry, it's really a product of the different densities of the individual components. Okay, so maybe it's worth just reminding ourselves what the density of the Laplace distribution is. So let's just kind of fence off some places to write reminders. So with the Laplace distribution, its density, one-dimensional, is 1 over 2 lambda e to the minus absolute value of y over lambda. Okay, so remember lambda is just the scaling factor. And so coming back to our calculation, what we'll get is that we've got this 1 over 2 lambda, so that's like epsilon over 2 times the global sensitivity. I'm going to save myself some writing by letting capital delta be this like global sensitivity. It's going to make the equations a little easier to read if I just use that notation.